I welcome all of you to the class. In today's class, we'll be doing few numerical problems based on the concept of inclined loads on doubly symmetric beams and on the concept of the bending of the unsymmetrical beams. First of all, let's do few problems on the concepts of the inclined loads on doubly symmetric beam. The question in front of us is that the question says we have a 4-meter long cantilever beam constructed from an IP and 500 section. As far as these IP and UPN sections are concerned, in the branch of structural mechanics of structural engineering, these are well-known terms, and these sections are well-known sections whose properties are already defined to us. Okay, so what is given to us that we have a cantilever beam, its length is 4 meter. This beam of length for 4 meter, span 4 meter, made of IPN section, IPN 500 section, is subject to a 45 kilonewton concentrated load at its free end in the vertical direction along the negative y direction. Okay, because the beam is very narrow compared to its height, its moment of inertia about z-axis is much larger than its moment of inertia about y-axis. This is quite evident because when we talk about the moment of inertia about y-axis, about z-axis, okay, that will be equal to moment of inertia about z-axis is integral of y square dA, and moment of inertia about y-axis will be equal to integral of z square dA. Fine, when we take a small area element. Okay, since as far as the y coordinate is concerned, the y is more because the beam is narrow. Okay, it means its depth is more as compared to its thickness. Okay, y coordinate is more as compared to the z coordinates. Therefore, iz is greater than iy. Iz is greater than iy. This is given to us. Right? Now the question says, determine the maximum bending stress in the beam if the y-axis of the cross section is vertical and therefore aligned with the load P. This is case 1. In case 1, it says that what is the maximum bending stresses in the beam if our y-axis is the axis along which the load is applied, if the line of action of the load matches with the y-axis. This is part A. And our part B is determine the maximum bending stress if the beam is inclined at an angle alpha equal to 1 degree to the load. A small inclination can be caused by imperfections in the fabrication of the beam, misalignment of the beam during construction, or movement of the support structure. So these are two cases. In the first case of the beam, our beam is subjected to a load of 45 kilonewton. The line of action of the load is along the negative y-axis. The y-axis matches with the line of action of the load. This is case A. And as far as the case B is concerned, in case B, the situation is different. The beam is misaligned. The load continues to be along y direction, negative y direction, but now the axis of the beam is now along, axis of the beam is at an angle 1 degree with respect to the load. Fine. So these are two cases. In both the cases, we have to determine what is the maximum bending stresses when the beam is aligned and when the beam is not inclined. It's having an angle of inclination of 1 degree. Fine. So first of all, let's solve the case number 1. We know whenever the beam is inclined, when the beam is inclined for case A, at that time for inclination case, when the line of action of the load acts along one of the axes of the beam, at that time we know that the maximum bending stress sigma is equal, we have the formula for it. Fine. And for us, as far as sigma is concerned, sigma is equal my m y za This is ZA divided by IY minus MZ YA divided by IZ. This is the formula we already know. Okay, we have to make use of this formula to find the maximum, to find the stresses, the maximum bending stresses. But if you look at the bending stresses, if you look at the bending stress, sigma Y, sigma Z, okay, if you look at these bending stresses, first of all, this is applicable when the beam is inclined. Okay, this is the case for the inclination. This is for case B. For case A, what is very important for us, very important for us, is we know that sigma is equal, we will directly use the fluxural formula, sigma is equal to my divided by I. Okay, in fact it's minus, okay, divided by I. Fine. And this is the case, this is the maximum bending stress that occurs in the beam when the beam axis is not inclined, when the beam axis matches with the line of action of the load. Fine. And where is the maximum value of sigma? Since the value of I is constant, the value of sigma will be constant at the point where our Y is constant, Y is maximum, as well as our M is constant, M is maximum. We know in case of a cantilever beam, the maximum bending moment occurs at the fixed end. Okay, and as far as, therefore we will write sigma max for case A, sigma max is equal M max, whenever M is maximum, M max Y max divided by I. I is the moment of inertia about the neutral axis. That's equal. If you look at your M max, maximum, that's at the fixed end, and its value will be equal P into L. Fine. Its value will be P into L. This is the moment that's at the fixed end, multiplied by the Y, distance from the neutral axis. The distance from the neutral axis, we know the maximum bending stress occurs at the top and at the bottom. Fine. So at that time, if this is your total H, okay, then the value of this Y has to be equal to H by 2, because at the top and at the bottom end, the compressive stresses or the bending stresses are maximum, divided by I. I is the moment of inertia. Fine. Therefore, the maximum bending moment, maximum bending stress will come out equal, this is 45 kilonewton. We will write 45 kilonewton multiplied by length. Its length is 4 meter, that is 4000 mm, 4000 mm into H by 2. As far as the total height is concerned, its total height for an IPN section, you should always remember, for an IPN section, as far as this height is concerned, this height is total 500 mm. Okay, this is already given to us. When, as it's given here, IPN 500. Okay, IPN 500 section means that its total height is, or total depth is 500 mm. So we'll write here H by 2 is 250 mm. So this is 250 mm divided by I. Okay, we need not to calculate the I, because as is given here, see table E2 for appendix E. The properties like its moment of inertia, its product of inertia is always given. Okay, so in your examinations, you can carry the charts, or you can in fact carry what's known as the you will be given the data. Fine. So its moment of inertia is 68,740 centimeter is for 4 centimeter 4. You can take units based on your choice. Okay, in fact, if you are not given the data, you can calculate it now. Okay, in fact, it will be given. Fine. So that is equal, the maximum value of the bending stress will come out equal 65.5 megapascal. 60.5 megapascal is the maximum bending stress. And where will this maximum bending stress occur? Okay, we know for a beam which is subjected to pure bending, at the top surface this will be compressive, that is it will be minus 65.5 megapascal, and at the bottom it will be tensile, that is plus 65.5 megapascal at the bottom. Okay, so as far as this overall analysis is concerned, as far as the overall answers are concerned, when the beam is not inclined, when the beam is subjected to the pure bending, at that time we can clearly say that the maximum bending stress to which the beam will be subjected is 65.5 megapascal. So we'll write it over here. So in our case number one, I'll write it over here. So in case of case number one, the maximum bending stress sigma max is equal 65.5 megapascal. Okay, fine. Now let's go to the part B. This is the maximum bending stress that occurs when the beam is not inclined. Now let's go to the inclination when the beam is inclined, that is this case. Let's take this case B. In case of case B, what is given? That now the load is inclined. Now the load is inclined about the y-axis. Fine, the load is now inclined, so we can definitely resolve it. We can say this load can be resolved into two components. It's having one component like this, and another component will be perpendicular to the y-axis, that will be along z-axis like this. Okay, so the load along this axis will be P cos of alpha, and the load along this direction will be P sine of alpha. Fine. Now the load is now inclined, so in this direction you are having P sine alpha, and in this direction you are having P cos of alpha. Fine. In case of this is not inclined, be careful, inclined is this. Fine, case B. Now what will be the moment? You have two forces. Now you have force along z-axis and force along y-axis. A force along z-axis will certainly create a moment. Okay, and if you draw a radius vector from here, and this z, a force along z, that is P sine alpha, will try to rotate the beam, and its sense of rotation, if you curl your fingers in this direction, your thumb will be in the negative y direction. So we'll write moment along y direction will be equal, moment along y direction will be equal minus, why minus? Because it's along negative y direction, minus P sine alpha into force arm, that is L. Fine. So we know the value of P. We know the value of P. The value of P is how much? 45 kilonewton. So it is 45 kilonewton sine of 1 degree, and length is 4 meter. 4 meter. The unit is kilonewton. Okay, so you have kilonewton and meter. Fine. So this comes out equal to minus 3.14 minus 3.14 kilonewton meter. Minus 3.14 kilonewton meter is the moment along y-axis. Okay, now calculate the moment along z-axis, that is mz. As far as mz is equal, the moment along z-axis will be created by this P cos alpha. Okay, this P cos alpha will now try to rotate the beam in this direction, in the downward direction. Okay, if you curl your fingers, your thumb will be in the negative z direction. Okay, that's why this will be equal to minus P cos of alpha into L. That will be equal minus P is 45 kilonewton, cos of 1 degree, cos of 1 degree multiplied by length is 4 meter. So it will be units will be kilonewton meter. Okay, so mz comes out equal minus 180 kilonewton meter. Minus 180 kilonewton meter. This is the value of moment along z-axis. This is the value of moment along z-axis. Okay. Then after calculating the moment along z and moment along y-axis, we calculate the tan of beta. That gives us the angle of inclination of the neutral axis. The value of tan beta is equal my iz divided by mz iy mz. Okay. And that is equal, as far as iz and iy are concerned, they are the beam properties. They are already provided in hand. So we'll write this as my moment along y-axis minus 3.14 kilonewton 3.14 kilonewton meter into iz. As far as iz is concerned, the value of iz is equal 68,740 centimeter raised to power 4 divided by my, that is minus 180 kilonewton meter multiplied by the moment of inertia, that is 2480. This is given to us. Okay. Centimeter raised power 4. So once you calculate, the value of beta comes out equal tan inverse of this, that is 25.8 degree. The value of beta is 25.8 degree. That's already given to us. So this NN represents the neutral axis now. Okay. That is when the beam is inclined. So be careful. This is something very, very important. When the beam is inclined, when the beam axis is inclined by 1 degree, when the beam axis is inclined by 1 degree, the neutral axis changes by 25.8 degree. So a slight change in the beam axis is responsible for a huge change in the neutral axis. Now the neutral axis initially was along z axis. Now the neutral axis is at an angle 25.8 degree with respect to the z axis. So that is very, very important thing. Now, where will the maximum bending stress occur? Okay, that's to be seen. Sigma max, since now we have to calculate the maximum bending stress. The maximum bending stress occurs at the points A, it occurs at the point B, at the top, at the bottom. You should always remember, at the top and at the bottom, the bending stresses are always maximum. Fine. Values are same. At the top surface, you will be having compressive. At the bottom surface, you will be having what you call as the tensile. Okay. What is the formula in case of inclined beams? In case of inclined beams, we will write stress at point A. We already have the derived formula. Sigma A is equal my za divided by iy minus m z ya divided by iz. Okay. So do we know the value of my? Yes, we know. The value of my is minus 3.14 kilonewton meter. Okay. Then we should know the value of ZA. What is the value of ZA? The value of ZA means how far is this point A from Z axis? That is, what is this distance? This distance is also given to us from the beam properties. Okay. All the properties are given to us. Okay, because this IPN's 500 section, it's all properties are given. As far as the ZA is concerned, this ZA is always minus 90. Since this along negative Z axis, it is minus 92.5 mm. Minus 92.5 mm. So here we will write ZA is minus 92.5 mm. Dimensions of beam are always given because the standard beam. How much is its moment of inertia about y-axis? That is also given. That is 2480 centimeter raised to power 4 minus. How much is the moment along z-axis? We have already calculated. That is minus 180 kilonewton meter multiplied by YA. How far is this point A from here? It is 250. Okay, because we know this IPN 500, total distance is 500. So this is 250. 250 mm divided by moment of inertia about Z axis. That is given 68,740 centimeter is for 4. So that comes out equal 77.2 megapascal. So this is 77.2 megapascal is the stress at point A. The stress at point B will be same as stress at point A, okay? But it will be mines. Here it's tensile, here it will be compressive. Fine. So it means, look what is happening. Initially, when the beam was not inclined, at that time we had stress at point A at the top surface. In case A, the stress at point A was equal, it was equal to 65.5 megapascal. 65.5 megapascal was the stress at point A when the beam was not inclined. Now when the beam is inclined, at that time the stress at point A comes out equal to 77.2 megapascal. The stress has increased. A little misalignment of 1 degree is responsible for an increase in stress, compressive stress, for an increase in bending stress from 65.5 megapascal to 77.2 megapascal, which is around 18% increase in the stress. So there is around an 18% increase in the bending stress by just 1 degree misalignment on the beam. So a 1 degree of the misalignment is responsible for how much of the increase in the bending stress? 18 degree. Number one. Number two is when you calculate the value of sigma A using this formula, it comes out to be positive. So it means here the force will be tensile. And at the bottom, the stress will be mines, that is compressive. The stress at point B becomes compressive. So look what is happening. At point A, when the beam was not inclined, the top surface was under compression and the bottom surface was under tension. But a little 1 degree misalignment is changing the nature of the stresses. At top A, you will have the tensile. At top B, now you will have the compressive. Apart from changing the directions of the stress, it's also causing an increase in the stress by around 18%. So this is the fact that a little misalignment of 1 degree is responsible for changing the neutral axis by 25.8 degrees, 25.8 degree and increasing the stresses by about 18%. So this is how we actually deal with the questions which are based on the misalignment. We have now a channel section UPN 220, which is subject to a bending moment of 2 kilonewton meter, but this bending moment of 2 kilonewton meter is at an angle theta equal to 10 degree to the Z axis. We have to calculate stress at point A, we have to calculate stress at point B, and we have to find the position of the neutral axis. Okay, this question will be solved based on the formulas and the concepts we derived for bending of the unsymmetrical beams. The problems of unsymmetrical beams are solved in the same way as the problems for the symmetrical beams. So as far as this C section is concerned, the properties of this C section that are given to us are, first of all, it's centroid. Where is it centroid? This centroid for a C section UPN 220, okay, is given to us. The centroid is at a distance of 2.14 centimeter from the Z axis. C is equal to 2.14 centimeter. Okay, the distance of the centroid C is located on the axis of symmetry at a distance 2.14 centimeter. Fine. So that is, this is at a distance of 2.14 centimeter. This is what is actually given to us. So we need not to calculate the centroid for this UPN sections. This data will already be in hand. We are also given the moment of inertia about y-axis. Iy is given to us 197 centimeter raised power 4, and Iz is also given to us 2690 2690 centimeter a raised to power 4. These two data are given to us. Okay, so let's first of all find the coordinates. Coordinates of point A based on the geometry of the C section. This is a standard U section. Its all dimensions are given to us. Since from here to the top the total is 220, so YA, the distance of YA will be 110 mm. We will also given, as far as the ZA is concerned, how far is Z from this point C. Okay, as far as ZA is concerned, the value of ZA is 221.4 minus the value of ZA this sectional distances, this section, the BE or DA for this section is 80 mm. It is 80 mm, and from here to the centroid C, the distance is 2.14 centimeter as already given, that is 21.4 mm. Therefore, from C to point A, okay, along Z axis, the distance will be minus 80 mm plus 21.4 mm. That comes out equal minus 58.6 mm. That is ZA. Rest of the dimensions, we have YB. It's again minus 110 mm, minus 110 mm, because total span is 220 mm. ZB, distance to ZB is 21.4 mm, and YD, we can write coordinate YD is equal to YA because they are in the same line. ZD is equal to ZB. ZD is equal to ZB. YE is equal to YB, and ZE has to be equal to ZA. Fine, these all are in the same line. Now look at the moment M. It can be resolved into two components. We'll have My will be equal to 2 kilonewton meter sine of, that is 2 kilonewton meter sine of 10 degree. So My comes out equal 0.347 kilonewton meter. 0.347 kilonewton meter. And Mz, the moment along Z axis, is 2 kilonewton meter. It's 2 kilonewton meter cos of 10 degree. Cos of 10, that comes out equal 1.97 kilonewton meter. So we know the value of My and Mz. Now directly use the formulas. As far as the formulas are concerned, formula for sigma A, stress at point A, is equal My Za divided by Iy minus Mz Ya divided by Iz. So we know all these values. Once we substitute, the value of sigma A comes out equal minus 18.34 megapascal. Minus 18.34 megapascal. And the formula for sigma B for us is equal My Zb minus Mz Yb. This is Iy and Iz. We just have to change the coordinates. Rest will be same. These are the same formulas. In place of Za, we are writing now Zb. That's okay. So once we substitute the values, it comes out equal 11.8 megapascal. 11.83 megapascal is the stress at point B. After calculating the stress at sigma A, stress at sigma B, okay, we can also calculate the value of sigma D. We can calculate the value of sigma B by making use of these formulas. Okay. Also, as far as the tan of beta is concerned, to find the neutral axis, the formula is Iz by Iy tan of theta. Okay, we have already derived this formula, so that comes out equal, beta becomes equal, beta is equal 67.4 degree. This is where the neutral axis will be. So your moment is along 10 degree, so your neutral axis will be at an angle of 67.4 degree. The procedure for solving this question is more or less the procedure for solving the previous type of questions. So this is how unsymmetrical beams or beams subject to incline loading are to be solved. We'll continue with the more problems hopefully in the next class. Thank you.